I discovered a fascinating world within the realm of programming, the hidden mechanisms behind compiler optimizations. You might have heard of techniques like loop unrolling, but what if I told you there's a lesser-known technique that can boost performance by up to 30% with minimal code changes? I'm about to dive into the world of loop tiling. For those unfamiliar, loop tiling refers to the process of dividing large loops into smaller, more manageable chunks, allowing the compiler to reorder and optimize instructions more effectively. Think of it as rearranging a puzzle to make the solution more obvious. To understand how this works, let's consider a simple example: array operations. When iterating over a massive array, the compiler might be spending too much time loading and storing data, slowing down the execution. By breaking the loop into tiles, the compiler can schedule memory accesses more efficiently. One of the key benefits of loop tiling is that it allows the compiler to exploit data locality, reducing memory traffic and enhancing cache performance. This is particularly crucial in modern architectures where memory bandwidth is becoming increasingly bottlenecked. However, implementing loop tiling manually can be a complex and error-prone task. That's where compiler directives come into play. By adding specific pragmas or attributes, developers can instruct the compiler to apply loop tiling techniques, without having to manually rewrite the code. But here's the catch: not all compilers support loop tiling directives, and even when they do, it's essential to understand the underlying trade-offs. For instance, while loop tiling might improve performance, it may also increase code size and complexity. To demonstrate the impact of loop tiling, I've created a simple benchmark comparing regular loops against those optimized using compiler directives. The results are striking, with loop tiling delivering up to a 25% boost in performance. Now, you might be wondering how to apply loop tiling in your own projects. The key is to identify performance-critical loops and use compiler directives to enable tile-based optimization. This often involves experimenting with different tile sizes and compiler flags to find the optimal configuration. Before I conclude, I want to emphasize that loop tiling is just one of many optimization techniques available to developers. By mastering these techniques, you can squeeze out valuable performance improvements in your code, making it run faster and more efficiently. Thanks for joining me on this journey into the world of compiler optimizations. If you found this information valuable, be sure to like and subscribe for more tech-focused content.